Well, today we're going to talk about root locus and go over a couple examples. So what exactly is a root locus? Well, it is a representation, a visual one, of how a closed loop system reacts and changes based upon the type of gain that affects the closed loop poles. And overall, we're just trying to see how the stability of a system works. When looking at what exactly is a root locus and how to make one, visually there's at least 7 for sure rules to look at. First one is locating the open loop poles and zeros in the S-plane. After that, we want to find out how many root locus branches there are. With that, we look to see if, look at the n, the p, and the 0, in which case n is the number of root locus branches, p is the number of finite open loop poles, and z is the number of finite open loop zeros. And so based upon those, we can figure out how many root locus branches are. The n and the p will be equal if p is greater than z, and n will equal z if it's inversed and z is bigger than p. So then our third rule is identify and draw all the real axis root locus branches. Following that, we'll find the centroid of the angle of the asymptotes. This, again, is dependent upon what n, p, and z looks like. In this case, there are about 4 examples of what it can be. And then in the end, how our centroid is found is by dividing the sum of real parts of finite open loop poles subtracted from the real part of finite open loop zeros and dividing that all by p minus 0. And then to find the angle, that can also be done. Fifth rule is finding the intersection point of the root locus branches with an imaginary axis, followed by finding breakaways and break-ins. And so with that, that's our general gist of how we're going to draw these root locusts. Let's look at one example here of 1 over s squared plus 3s. This could also be seen as s times s plus 3 for that denominator. And when we look at that, based on the numerators, there's no polynomial, the polynomial has no zeros. When we look at the bottom, the denominator, we see that it does have 2 poles, one at -3 and 0. And then based off of that, we can figure out that it has 2 branches in the locus, as well as that it will go to infinity for k and s in terms of our q. And with that, a graphical visualization is we're going to put those poles at -3 and 0. And then from there, based on there being 2 branches, we're going to go towards each other and then split up and down based upon it being symmetrical. We're going to look at one more example. This is 1 over s cubed plus 5s squared plus 6s. Again, the numerator has no zeros. The denominator has 3 poles this time. So we have -3, -2, and 0. So we're going to have 3 branches of the locus. And this time it's going to be a little bit different where instead of going towards each other, due to having the q of 3, we're going to have the leftmost one starting at -3 go out. And we're going to have that -2 to 0 come together. And then the way there's those arches, that's where we get those breakaway points, and we find the angle for the asymptote. And overall, that's kind of how root locuses work. They can get more complex. They can also get easier, but overall, we're just checking out the symmetry, the system stability. And here are my resources. Thank you for listening.